Welcome to Electro-Knowledge. Today, we're going to talk about a real game changer for circuit analysis, a tool that lets you take a big tangled mess of a circuit and shrink it down into something incredibly simple. I know, it sounds almost too good to be true, right? But it's absolutely possible, and the key is something called Norton's Theorem. Honestly, getting this down is going to make your life as an engineering student so much easier.
Electro-Knowledge. Power up your concepts.
So here's our game plan for today. We'll kick things off by talking about why this is so powerful. Then we'll get into what the theorem actually is. After that, we'll break down the 5-step method you can use every time, apply it to a real circuit, see how it relates to its famous twin, and then we'll wrap it all up with the key takeaways.
Okay, let's dive right in. Before we even get into the nuts and bolts of how Norton's theorem works, I think it's super important to understand why you'd even want to use it. Why add another tool to the toolbox? Well, the big idea here is all about efficiency. I mean, think about it like this. Say you're designing an amplifier, and you want to test how it works with 10 different speakers. Without this theorem, you'd be stuck doing 10 separate, really complex calculations. But with it, you just create one super simple model of your amplifier, and then you can plug and chug the numbers for each speaker in seconds. It saves a ton of time, and believe me, it slashes the chances of making a simple mistake. So, what exactly is this magical tool? Let's get to the official definition and see what's really going on behind the curtain.
And there it is. The theorem states that any linear network, and I don't care how many loops or sources it has, can be replaced by this simple equivalent. It's just a single current source running in parallel with a single resistor. That's it. From the perspective of anything you connect to it, that complex circuit and this simple one look exactly the same. And here's a little bit of cool history for you. This brilliant idea wasn't just a single aha moment. Back in 1926, it was developed at the exact same time, totally independently, by Edward Norton at Bell Labs over in the US and Hans Ferdinand Mayer at Siemens in Germany. Talk about great minds thinking alike. Okay, this brings us to the most important part of this whole explainer, the repeatable 5-step method that you can use every single time to simplify pretty much any linear circuit you come across. Think of this as your playbook. Step 1, we take out the component we care about, our load. Step 2, we find our Norton current, which is basically the max current the circuit can deliver. 3, we find the Norton resistance, which is the internal resistance of the network. 4, we draw our brand new simple circuit. And finally, step 5, we plug our load back in and get our answer. Let's see it in action. Theory is great and all, but this stuff really clicks when you see it work. So let's take these 5 steps and put them to the test on an actual circuit. Okay, here's our circuit. We've got a 12-volt source, a couple of resistors, and our mission, should we choose to accept it, is to find the current flowing through that 1.5 ohm load resistor on the far right. Now, we could use something like mesh analysis, but let's see just how much easier Norton makes this. All right, step 1, we just temporarily remove that load resistor. That leaves us with 2 open terminals, which we can call A and B. For step 2, we need to find the Norton current, IN. All that is the maximum current that the rest of the circuit can push out. To find it, we just connect a wire, a short circuit, between A and B, and calculate the current flowing through it. So to get that number, we can use the current divider rule. We figure out how the total current from the 12-volt source splits between the different paths. And when you do the math, it turns out the current going through our short circuit is exactly 2 amps. And just like that, that's our Norton current, IN. First piece of our puzzle is solved. Next up, step 3, finding the Norton resistance, RN. For this, we go back to our circuit with the load still removed. And what we have to do is turn off all the power sources. For a voltage source, like our 12-volt one, turning it off just means we replace it with a plain wire, a short circuit. If we had a current source, we'd replace it with a gap, an open circuit. So, with our 12-volt source replaced by a wire, if we look back into terminals A and B, we can see that the remaining resistors are in a parallel combination. We just calculate the equivalent resistance of that arrangement, and we get 4.5 ohms. And there you have it. That's our Norton resistance. We now have both pieces of our puzzle. And now for the best part. Step 4 is where the magic happens. We draw our brand new super simple Norton equivalent circuit. It's just our 2 amp current source in parallel with our 4.5 ohm resistor. This little two-component circuit behaves exactly like that bigger one we started with. Then, for step 5, we just reconnect our 1.5 ohm load resistor.
Now look how easy this last calculation is. We've got a basic parallel circuit, so we can use the current divider rule one more time to find the current going through our load. We plug in the numbers, our 2 amp Norton current and our 2 resistors, and the math gives us a final answer of 1.5 amps. Done. So much simpler than analyzing the original circuit.
Now, Norton's theorem doesn't live in a bubble. It actually has a very famous twin that you've probably heard of, Thevenin's theorem. Let's take a quick look at how they're connected.
Here's the most important thing to know. The resistance calculation is exactly the same for both theorems. That whole process of turning off the sources and finding the equivalent resistance gives you a value that's both the Norton resistance, Rn, and the Thevenin resistance, Rth. They are always equal. This really just shows that the two theorems are just different sides of the same coin. Thevenin gives you a voltage source model, and Norton gives you a current source model. And you can flip between them super easily just using Ohm's law. It makes them an incredibly flexible pair of tools to have.
Okay, let's bring it all home and quickly recap the key takeaways. If you can just remember these 3 core ideas, you'll have a really solid handle on Norton's theorem.
So, it all boils down to this. First, find that short circuit current across the terminals, that's your Norton current, IN. Second, find the equivalent resistance looking back into the terminals with all the power sources off, that's your Norton resistance, RN. Finally, your new circuit is just IN in parallel with RN. If you've got that down, you can tackle any linear circuit.
And I'll leave you with one last thing to think about. We often get stuck thinking about circuits in terms of voltage, but Norton's theorem really forces you to shift your perspective and think about current delivery. So how does that change how you approach a problem? How would you look at a complex electronic system differently if you were focused on the current it can supply? It's a really powerful way to reframe things.
I really hope this explainer helped make Norton's theorem a little less intimidating. If it did, please hit that like button, subscribe to ElectroKnowledge for more circuit analysis tips, and share it with a classmate who might find it useful. Thanks for watching, and I'll see you in the next one.
Thanks for watching. Like, share, and subscribe to ElectroKnowledge for more electrical concepts.